Uh, Hi, Professor.
Hello,
Hello.
be here.
Thank you, Professor, for accepting the invitation to join
Thank you for
us.
the invitation, Seth.
Hi, everyone. Today I will be hosting the famous mathematician Hugo Duminil-Copin. Before we start, let's know some of achievements of this scientist. So, the Professor Hugo Duminil-Copin is a French mathematician. He is a professor at the Faculty of Science of the University of Geneva and permanent professor at the Institut des Hautes Etudes Scientifiques. The Fields Medal is awarded to him in 2022. Hugo Duminil-Copin works focuses on the mathematical branch of statistical physics. He uses idea from probability theory to study the critical behavior of various lattice models, such as Ising and percolation theory. These mathematical objects describe a number of physical phenomena. The professor received many awards and did many important researches. There are many other achievements of this scientist. It's great honor for me to speak with you, Professor.
Thank you very much.
I take your time and I ask you a few questions, which many followers of this channel and mathematics lover are looking for. So, uh, I start by the first question. Since you've been awarded Fields Medal in 2022, can you tell us more about this Fields Medal and what is your experience when you get it?
Yes, so the Fields Medal is an award in mathematics. It's given every 4 years to at most four mathematicians, between 2 and 4 usually. And it's considered as the most prestigious award in mathematics. It's sometimes compared to the Nobel Prize, but there is something very special about the Fields Medal is that you cannot win it when you are over 40. So you need to be less than 40 years old. At the very beginning of the prize, in fact, it was imagined as something that would be an encouragement to do more research. And now it's actually an achievement award. I mean, rewarding what you already did, but it's also in some sense in the middle of your career. So you still have a lot of things to show. So for me, it was a kind of a funny experience because I learned about the fact that I was receiving the award in January. So it was officially given on the 5th of July, but you are told in advance and you have to keep it for yourself. So it was very strange. It was actually funny because the announcement went into my spam. So it took me a few more days to actually have the official announcement. I guess something like you got an award is something that goes automatically in spam. So so I was told a little bit later, but then I kept it for myself. And on the 5th of July, I could finally enjoy with my collaborators, with my family, with the mathematical world, all this joy and honor that this represents. I mean, for me, it's a big honor, and I'm very happy for myself, but also for my community, my collaborators, and everybody who works with me. You are muted, Mustafa. Mustafa, you are muted.
So, uh, Thank you, Professor. Can you give us a glimpse of your work?
Yeah, so I work in statistical physics, as you said. So statistical physics is a study of very complicated systems, like gas, for instance, so gas in a room. And what I do more precisely is I study what we call phase transitions, which are like brutal change of behavior in these complex systems. For instance, imagine you vary the temperature or the pressure, and you start from liquid water. When you reach a certain point, it becomes like vapor or it becomes solid. It's a drastic change of behavior. It's a phase transition. So I study phase transition from the mathematical side. So I'm going to do mathematical caricatures. We will probably talk about it later. So kind of what we call mathematical models. and I study mathematically these models to try to explain why there is such a brutal change of behavior in my system.
So thank you. You have showed the connective constant of the hexagonal lattice and your doctoral thesis. Can you tell us more about this constant?
So this is, for instance, one example of a mathematical model. So imagine you want to understand a polymer, right? So a polymer is a long chain of molecule. It's a molecule which is a very long molecule due to the fact that it's an addition of many, many monomers. And you can think of this when you draw it in your space or in the plane, you can think of it as a path which is avoiding itself, right? I mean, you cannot have two monomers at the same place. So if the polymer is already passing somewhere, it cannot pass back by the same place. So this is called a self-avoiding path. And you can try to model mathematically a polymer by defining by simplifying a little bit the model and imagining that this path is drawn on a honeycomb lattice, on a lattice made of hexagons. Like, if you look at honeybees, like you look at this, shape that you see when you look at bees hives. So you imagine you are on the hexagonal lattice and you try to see how you can draw self-avoiding path on this lattice. You start from a point. So it's a cool exercise if you want to try. You can try to count how many paths of length 1 you can do. Well, you have 3 neighbors, so you have 3 ways. Of length 2, you can imagine that, so you have 3 tries for the first try, and then you have 2 for the next one. So you have now 6 self-avoiding walks of length 2. And I encourage you to try a little bit higher numbers, and you will see that the number of self-avoiding walks grows very fast. It grows exponentially fast with the length. And it's very complicated to compute how many self-avoiding walks of length n you have. Even for n equal 100, I think the best computers can barely compute this number. So it's natural to try to see how fast the number grows when n goes to infinity. And what we proved with Stanislas Smirnov is that we proved that the number of self-avoiding walk of length n, it grows exponentially fast, but in fact it grows roughly like square root of 2 plus square root of 2 to the power n. And it's a super cool result. So it's kind of a counting result, right? It's what we call combinatorics. You are counting the number of objects having this and this property. So here you are counting the number of self-avoiding walks of length n. But in order to find this kind of magical square root of 2 plus square root of 2, which is kind of a funny number, you actually need to connect the question of self-avoiding walks to other fields of mathematics, in particular, what we call a discrete version of complex analysis. So some of your readers followers probably know about complex analysis. It's the study of functions that are complex valued and have a complex variable. And you have a whole theory of that. And actually, we make a connection between this very combinatorial question of counting number of paths on the hexagonal lattice to the world of complex analysis. And using this connection, we can prove this very cool number.
If there is some relation between this connection of lattice and the path integral and topological theory.
So that I'm not sure I know about that. So the self-avoiding paths in general, they appear in many models of statistical physics. So it may very well be that it connects to some of what you know in other fields. The computation of the square root of 2 plus square root of 2, this combinatorial question, it's mostly motivated by the understanding that this square root of 2 plus square root of 2 is related to what we call the critical point of the self-avoiding walk model. Imagine you want to understand the behavior of polymers. Sorry. Somehow you can try to see when you put these polymers in a solvent, depending on the properties of the solvent, whether these polymers have a tendency to kind of get close to each other, like, kind of only try to get as small as possible, or on the other hand, whether they try to extend as much as possible. And these type of models, they were introduced by a Nobel Prize winner, Paul Flory. So he's a chemist, he was not a mathematician. And this scaffolding-walk model, at least this way of looking at the model, these combinatorial questions, they are related more to this chemistry question. So it may be that there are other connections I don't know about, but here the main motivation is understanding the spatial location of polymers.
Thank you. Next question. What is the relationship between the probability and theory and phase transition and statistical physics?
Yeah, so that's a very good question. So you see, I told you I want to understand the phase transition in statistical physics. So I want to take a complex system, let's say a magnet, for instance, and I want to understand whether it's magnetized or not. And this you see, it's a very complicated question. So you can simplify a little bit the question by introducing randomness in the system. In some sense, it's kind of say, imagine you throw sand on a beach, you throw it, or in the desert, you throw it into the air, and there is wind. If there is wind, you agree that basically the sand globally is going to be pushed in the direction of the wind, and it's going to follow the wind. Now, if I really want to keep track of the behavior of every single one of the grain of sand, it's going to be a very complicated question, because when I throw it in the air, maybe it goes in a slightly different direction with a slightly different speed. Maybe it actually collides with other grains of sand. It's a very complicated system. So what you do as a statistical physicist is that you introduce probability. You are going to say, okay, I'm not going to look at exactly the behavior of each grain of sand. I'm going to rather try to look at the typical behavior. I'm going to pick one grain of sand at random and look at how it goes. So here, for instance, is an example where using probability, in some sense, simplifies your life, because you don't have to understand every possible behaviors. You have to only understand the typical ones. And this is what we do in statistical physics. So that's a connection. Phase transition being a very complex thing, like this brutal change of behavior, it's very subtle, it's very complex to understand. So we use probability to simplify a little bit our life and look at typical behaviors and try to understand for these typical behaviors why there should be a phase transition.
Thank you for this question. It's amazing to link the mathematics and physics. I suppose that this statistical physics is the link between mathematics and physics and real life.
It's one of the links. I mean, it's a typical example where mathematics is very successful at describing physics, right? I mean, there is always this question of why is mathematics so good at describing what happens in physics? Why is it such an important tool in physics? So in statistical physics, it's one of the prime examples where it's super useful. You have different type of physics, right? I mean, quantum physics is going to be studying the infinitesimally small things. You have Einstein general relativity. You have all these different theories, and you have, like, when you look at complex systems, you don't want to be following Newton laws. It's going to be too complicated for a gas to understand, the behavior of each one of the atoms or the molecules in the gas. So here you use statistical physics. And here again, even exactly like in the other domains of physics, mathematics is super powerful at helping describe the world. In statistical physics, again, mathematics, and in particular probability theory, is a super powerful tool that is exactly giving you the tools you need to describe what happened in the physical phenomenon. So we are lucky.
Well, yes, we are looking so much. Next question. If Can you tell us more about what is this Ising model, mysterious Ising model?
Yeah, so I mean, the Ising model, to give you a context, it's yet another model of statistical physics. So it's supposed to explain, it's a mathematical caricature again of a physical phenomenon. And in the case of the Ising model, it's a caricature for what we call cooperative phenomena. So systems where the elements of the systems have a tendency to try to cooperate. And there is a typical example. Actually, it's not the best model for this, but it was motivated by that in the origin. So you can try to model magnets. So you think of a magnet as being a collection of small, what we call dipoles, which you can imagine as small magnets themselves, like tiny, tiny magnets. So now magnets have a tendency to align. So it's kind of the cooperation here. They want to cooperate and align in the same direction. But there is a temperature which is introducing some kind of disorder in the system. So there is a competition between the tendency for the small dipoles, the small constituents of your magnet to align, and the disorder coming from the temperature. So there is a model, a way to, if you want, simplify a little bit the picture, called the Ising model, where you basically imagine that your dipoles are on a regular lattice, for instance, your honeycomb, if you want, or the square lattice. It's a more standard lattice on which we define the Ising model. And again, you said that the dipoles have a tendency to align. The small dipoles, another simplification you do is that you kind of assume they only point north or south, which, I mean, if you look at magnets, a priori, they could point in any direction. Here you say that it's either to the north or to the south. It's the only two possibilities. And out of that, again, you introduce probability and you end up with a model which is called the Ising model. Now, what do you want to explain in magnets? Well, you want to explain, and this is actually an experiment you can do at home if you buy the right type of magnets. There are magnets for which this is doable with just a lighter. So what happens is that if you heat a magnet at a certain temperature, this magnet loses magnetization. What we say, it stops to be a magnet. So there are experiments you can find online where you have a magnet attached to something. You heat the magnet, say with a lighter, if it's the right magnet. Then at some point it reaches a temperature, it stops to be a magnet, so it stops being attracted, and just gravity make it fall. So it's a phase transition between a magnetized phase and unmagnetized phase. It's again a drastic change of behavior. It's the same atoms, the same molecules. It's just that depending on the temperature, they have completely different behavior. Either they act globally as a magnet or they don't. And so mathematically, with the Ising model, you try to explain why on Earth temperature should actually change something to my magnet. Why on Earth should it be that for very high temperature, this magnet stops to be a magnet, why at ambient temperature, it's actually a magnet and it has all the benefits we know. So the Ising model is a mathematical caricature for
that. Thank you. This is really a best model to explain some lattice and particle and molecular physics. Can you explain what is the problem within this Ising theory?
So what's the problem? I mean, is there a problem? I don't know. Maybe you mean what are the open questions in some sense? What we don't understand on the model. So this model, by the way, I should maybe have said, it's 100 years old. Okay, basically like date to date. It has been introduced roughly 100 years ago. So there have been, if you can guess, many things on the Ising model. And in particular, one thing which is true is that when you look at the Ising model defined on the square lattice, for instance, so really, you pave the plane by squares. There, things are very well understood. In particular, and this for your culture is something which is something to be remembered, one of the biggest achievements of 20th century statistical physics is due to Hans Zager. He's also a Nobel Prize, also in chemistry. And what he did is that he computed what we call the free energy of a magnet defined of the Ising model on the square lattice. So what's the free energy? If you want, it's the typical energy per unit of volume of your magnet. So it's something very useful. Once you have this, you can do many things. And so he computed that explicitly. It's a formula. You can find it on the internet if you look at the exact solution of the Ising model on the square lattice. And once you have this exact formula, you can do many things. So in some sense, what Hans Zager did is he solved what we say the 2D Ising model. But notice that there is a small caveat when you do that, is that magnets are three-dimensional. They are not two-dimensional objects. They are not infinitely flat. So the Ising model in 2 dimensions is interesting for many reasons, but you would like to understand what happens in 3 dimensions. This is much closer to the actual systems you have in mind. But there is no known exact formula for the free energy, for instance. What we actually expect is that there is no exact formula at all. You cannot express it with, like integrals, sine, cos, and all these standard formula, standard functions. So we are at least, maybe it's, of course, you should be careful when you say there is no, because it's very difficult to prove the absence of an expression. It's somehow simpler to prove the existence of the expression. You just have to give the example. But basically, I think it's a kind of common agreement, at least today, that there is no formula for this. So you need to find other ways of studying the Ising model. So we progress in this direction with my collaborators, but there are still many open questions in that direction for the 3-dimensional Ising model. In particular, there is something very important, is to try to understand what we call the critical exponents of the model. It's kind of something which is describing, it's kind of numbers that are describing the properties of the phase transition. So you want to compute them, and there is a lot of work both on the math side and on the physics side to try to get these exponents. And I guess there is still a lot of work ahead. This is one example, for instance, of an open question on the Ising model.
Yes, it's an open question. And what is your solution to this model of Ising?
I had solutions to some problems there, but of course, there are many other problems that I don't know how to solve. So I just don't have solution for those problems. Really, the Ising model, if you want, you should not think of it as one problem. It's just one object on which you can ask like an infinite number of questions. Of course, they are not all as interesting as, they are not equally interesting, but you have an infinite number of them. So you have an infinite number of problems, and then an infinite number of potential solutions. So to tell you, for instance, one thing that I solved on the Ising model, to give you an example maybe of what I'm working on. So on this 3-dimensional Ising model, with Michael Eisenman and Vladas Sidoravicius, so 2 colleagues, what we proved is the following. When you have a phase transition, there is a very natural question that you want to ask. And this question is this phase transition continuous or discontinuous? Because depending on the answer, you will see something completely different. So if you want the physics behind it, it's completely different. You enter in 2 different worlds. Let me give you an example of a discontinuous phase transition to tell you what that means. If you take water, liquid water, and you heat it, it reaches 100 degrees, let's say at standard atmospheric pressure, and then it becomes vapor, right? But one thing which is actually very important for all, for many motors, for instance, is that the vapor doesn't have the same volume, like the same amount of molecules of water don't have the same volume if they are liquid or if it's vapor. It's like 10,000, basically, the ratio between the two. I think it's something huge. So it takes much more room. So if I plug if I'm plugging the volume in terms of the temperature, it's increasing slowly. And then when I reach 100 degrees, boom, I need to go super high to put the dot of what is the actual pressure there, volume there. And then I carry on very high. So there is a discontinuity in the pressure, in the volumes. So this is typically a discontinuous phase transition. If you take a magnet and you hit the magnet, then, as I said, there is a phase transition. At some point, you stop being a magnet. But what you can do, which is a little bit more precise, is you can measure the strength of the magnet, right? I mean, magnets are not equally strong. There are magnets that are stronger than others. So plug the strength of the magnet in terms of the temperature. If you plug it, you hit, so the thing is going to decrease more and more. And what happens is that it's going to reach zero exactly at the place where it stopped being a magnet, and then it stays equal to zero. But here you see, when you plug the magnetization, what we call the magnetization, so the strength of your magnet, there is no discontinuity. It's continuous. There is still a change of behavior because you have no magnet, but the strength of the magnet decreases continuously to reach zero. Well, this is an example of a continuous phase transition. And that's what you see for magnets. That's what, by the way, Pierre Curie was a person who, so maybe not invented, I mean, discovered this phase transition. Apparently it was discovered before, but definitely he's a person who made the most compelling experiments in the end of the 19th century, like in 1895, to show that there is systematically this phase transition. So he saw that it's continuous. So what we did with Michael Eisenman and Vlada Sidova-Avicius is that we took the Ising model, so the mathematical caricature, the mathematical model, and we proved for this model that the phase transition is continuous. But notice we don't have this kind of exact formula that you have in 2 dimensions. So you need to prove that a certain function is continuous, but you don't know what is what we call the critical point. So you don't know where the phase transition takes place. You know there is one, but you don't know where. You don't have a formula for the magnetization. So you cannot just, check that this is a continuous function. So you need to cook up new tools and new techniques to prove that. But this gives you at least one example of a result that I proved with my co-authors, of course, for the Ising model.
Thanks for this answer. Following this simplification of the solution, it's possible to find a typical solution of the Ising model and the dimension, for example, in general.
So if you think of saying a solution in D dimension as finding a formula, for instance, for the free energy or the magnetization, it's something that some people try to do, right? Because in 2 dimensions, it was very successful. In fact, in 1 dimension, it's basically an exercise, maybe not very simple exercise, but it's an exercise to really derive everything explicitly. So it's natural to try to do it in dimensions 3, 4, and more. My take again is that it's probably a difficult question in the sense that it may even not have an answer. So I prefer not to think of understanding the Ising model via the tactic, if you want, of trying to compute explicitly the free energy and the magnetization. So I tried rather to find other ways of understanding the critical phenomenon, in particular of the Ising model. And in particular, you can do it in 4 dimensions or in 5 and more dimensions. It becomes, in fact, simpler than 3 dimensions. So there is this thing, the devil is in the details, or it's playing with mathematicians and physicists because you are interested in dimension 3. Dimension 2 is a place where you have these exact formulas where you can compute things explicitly. dimension 4 and higher are actually simpler because they have what we call a mean field behavior. I will not enter into detail, but it's a place where you can, again, solve things in a much better fashion, and you can describe much more what happens. It's actually especially interesting in dimension 4 because dimension 4, right, is actually the dimension of space-time, right? 3 space dimension, 1 time dimension. So it's connected. The Ising model is somehow connected to quantum physics there. It's not a very strong connection, but it was interesting to study the 4D for this reason, for its connection to quantum physics. But again, I mean, definitely the dimension which is the most interesting physically and mathematically is 3 dimension, and this is the hardest one. So in some sense, you know, we were both unlucky and lucky, because that means that we still have a lot of work to do and still a lot of things to try. But if you are looking for a solution of the Ising model in every dimension, basically my answer is 1 and 2, we have exact formula. 4 and higher, you should not look for an exact formula, but you can still describe the behavior fairly well. And dimension 3, we are in the
dark. Thank you. And following this question, what is the relationship between this model and Fortuyn and Castilian theory?
Now it's becoming technical in some sense. Let me try to give you the context first. So, you see, mathematicians, there is nothing that they like more than bridges. We like to make connections between different objects. And here, let me start the story by not mentioning at all magnetism. Imagine you forget completely what I said, or you didn't understand anything to what I said. I don't know. You know, I don't. But imagine you forget, okay? And we start again. But I choose a different story. I'm telling you, I'm actually interested in understanding porosity, like how a liquid, for instance, or a gas, goes through porous stone or coal. Or I mean, we like, as mathematicians, we like coffee, so we can, you know, you pour water in coffee grains, and you try to see how water goes through the grains. So you want to study porosity of a medium. There is a mathematical model for this called percolation theory, which consists in understanding, if you want, your medium. So is there a grain of coffee or the porous stone or coal, you want to understand it as a random maze. So in technical terms, mathematicians prefer to say as random graphs. So you imagine that in some sense the graph is telling you where is a connection in the graph are telling you where you can go, where the liquid or the gas can go in the medium. So it's an old theory. It's also dating back to mid 20th century to try to study the connectivity properties in percolation. And the thing is that there are many percolation models. If you Google, you know, percolation, you will see very cool pictures of different kind. All these models are describing kind of connectivity properties in your system. And basically, what you the connection with the Ising model is the following: is that you can understand the correlations between the different places in your magnet. You can actually rephrase that as connectivity properties in a certain percolation model. So you see, you take two things that are living in completely different worlds. Models that explain porosity of a medium, models that explain ferromagnetism, like magnets. But these two models, in fact, if you choose them properly, there is a connection, a bridge between the two models, and you can use then this bridge to study the Ising model using the percolation model, which is associated to it, which is rephrasing the correlation in Ising. And this model, it has a name. It's called Fortuyn-Castilian percolation. So that's the connection between the two.
Frankly, it's what you have done at this field. It's very impressive, really. We are waiting for you to win.
I'm not sure you should be impressed, but thank you. That's very nice.
We are waiting for you to win the Nobel Prize in physics one day.
You know, I mean, there is, you know, everybody is good as what he does. So, I mean, it's important to find what you are good at. You see, I'm good at creativity, like I'm good at creating new math ideas. Physicists are usually very good at creating new phenomenology, like understanding that something different is going to happen and so on. And Nobel Prize are usually recognizing this type of creativity, you know, finding that a certain material should behave like that or like that and so on. I'm much more like, okay, now you tell me it behaves like that. I can see it even in a lab. I want to understand why mathematically. You see, it's kind of a different job in some sense, and it's complementary. So I would definitely not even dare to hope to win the Nobel Prize. It's for different people and different creativity. Each one is complementary. That's what is beautiful in science, is that you need all different type of creativity and skills to advance together.
Good. So I have another question. What is your impact of your solution on the progress on mathematics and physics?
So, I mean, I like to think, I mean, of course, it's a difficult question because you are asking me to judge. I mean, of course, other people using what I do will answer this much better than I do. But at my small scale, I would say that probably one of the contributions is that these percolation models, that I mentioned, I told you there are many of them. And in some sense, until a few years ago, maybe 15 years ago, or 20 maybe, the understanding of these models was very limited. It was limited to models where we say the model is having a lot of independence, what we call Bernoulli percolation. In Bernoulli percolation, your maze, your random graph, is defined in such a way that in some sense the edges of your graph are independent of each other. And independence, when you are a probabilist, it's a very important tool. It helps you a lot. But when I mean a lot, it's really a lot. The problem is that percolation theory is connected to many other phenomena, but usually the percolation models that are connected to these other phenomena, they are actually dependent percolation models, meaning that the state of the edges are very dependent on each other. If I tell you here there is an edge, in fact, that it's going to give me information if there is an edge there. And so for this type of models, the theory of percolation was not so well understood. So when I arrived, I tried with my co-authors to kind of create momentum to try to say, okay, we have to understand these dependent percolation models, because if we want to use those models, it's good to make bridges. Actually, the bridge is not due to me. The bridge between FK and the fortune castilian percolation and Ising model dates to the 70s. But if you want to use it in a powerful manner, you need to understand very well the dependent percolation models, the fortune castilian percolation in particular. So we started from scratch almost and say, okay, we have to understand, to build up a whole theory of dependent percolation models. And that's what we did and what we are doing. And this has now impact because these percolation models, they are found in more and more places. And because there is now a theory of dependent percolation models, you can try to use those percolation models to say new things about these other phenomena. So I would say that it's the building up of this dependent percolation model theory, which is maybe the main contribution. And I hope it will have more and more applications and that it will inspire people. But I mean, of course, it's always difficult to know where research is going to go. And this is also why it's beautiful. You are again muted. Sorry. I'm trying to read on your lips, but it's not easy.
Good. Thanks. It's great. So I have another question. What is your advice to students to excel on mathematics?
I think one thing, it's a difficult question, right? Because every student is different, so he has his own weaknesses and his own strength. We all have. I mean, at every single level. It's not that you have, people that arrive and are absolutely perfect at everything. Sometimes you see this kind of machines like, I remember in my youth, there were like when I entered the École Normale Supérieure, for instance, which is a very elite school, there were people that were infinitely smarter than me. It was completely clear that we were not even from the same planet. They were much faster, much more efficient. They were not making mistakes. They knew how to use knowledge that they read in such an efficient way. But somehow maybe, I was more creative, or I was not. So everybody has his own strengths and weaknesses. So it's difficult to give an advice that would be valid for any student. But I would say that there is something to learn in math, which is important, because I don't think there is a single example of somebody solving a problem without loving this problem. You need to really be into it, to really want to solve the problem, because it's a long process. It's a difficult process. And it's going to come with a lot of moments that are going to be difficult, because you will make mistakes, because you will, go in wrong directions. So you need to be passionate about your problem. So this is something you can try to learn as a student. You don't need, Riemann hypothesis and try to prove the biggest conjecture in math to be motivated by a problem. It can be one exercise which is just a little bit too difficult for you at first sight. And you just, sit and try to solve it. And maybe it's going to take a day, maybe it's going to take a week. Sometimes it can even be, a problem you have, okay, I know how to do 1, 2, and 3-star problems from my professor. Let's ask for a 4-star problem. And maybe it's going to take me 2 months. I'm going to think once in a while about this problem, and maybe I'm going to solve it. And you have to learn to do that, to learn to kind of get passionate by a problem, try to see what you like, what you don't like, because it can depend a lot on the individual. And if you start to have this kind of passion for problems, then things are going to follow, because if you like a problem, you want to learn about what is going to allow you to solve it. So you are going to learn the material much more efficiently because you are motivated. You are going to, once you have this material known, you are going to be much more efficient to learn, neighboring ideas, which maybe are not even related to your problem. So having a goal and being able to be passionate about a problem, it's something very important in math. And maybe that's one advice I can give to students, is to find what they like in math and what they can be passionate about in math, and use this as, if you want, an engine that is going to make a motor that is going to make their car go faster.
Thanks, wonderful for the people and the students who want to excel in mathematics. Last questions. I have a question for the people who hate mathematics. Who can they change their mind for?
Yeah, that's a question. Yeah. I think many mathematicians would like to answer this efficiently. I'm not sure I will be one of those, but first I should say that usually when somebody tells you that he doesn't like mathematics, that he hates it, especially he hates it, it's usually that he hates the way it was taught at school. It's rarely that they don't like mathematics. It's that they don't like mathematics at school, right? Which is a very big difference. I guess that's your question, is how you make people enjoy mathematics at school. Because mathematics outside of school, I feel like many people have actually a very strong appetite for learning about the mysteries of this kind of arcane science, which is mathematics and all these beautiful results. So I think what people hate is really truly like math classes. There, it's difficult. I think maybe the answer to the previous question is still applicable, actually, even if you are not, a student in university. I mean, why a 6 or 7 or 10 or 14 years old student could not, enjoy trying to solve a mathematical problem? I don't think I don't think I met many mathematicians who enjoy just reading the solution to a problem. It's cool, there are nice proofs. That's true. But I mean, what you truly enjoy is actually trying to solve and find the solution on your own. And this is something which is not, so much in the middle of at the center of math teaching. So maybe trying to put this back, like just a taste of trying to solve a problem, rather than just, bombarding the student with theorems to learn by heart and things like that. I mean, it's not what I enjoyed, and I like math. So I guess that if you take somebody who is less inclined, who is less into math, imagine what it takes, what it gives on them, that to be bombarded by theorems. I mean, they are going to just hate it. It's normal. So maybe learning how to do math actually by yourself, like create your own math at every single level, it's actually something that can be, I guess, implemented. And maybe that's an answer. A terrible one, but
I hope for the people who hate maths hear this answer. Thank you, Professor, for these important informations, which we really enjoyed. Now, please, Professor, we will pass to the questions for the follower alive. Mm-hmm. If you have some time.
Yes, of course. Please ask questions.
So, what is your opinion from Ashraf Belkhomani? What is your opinion about Math Olympiad? Have you ever participated in it? And what kind of integral do you use in your work? Do you use partial integral differential equation too? So,
okay, so I mean there are more several questions, right? I mean there are two questions.
Three questions.
Let me start with what I think about Math Olympiads and whether I participated in it. I can tell you one funny story is that so in France, preparation to Math Olympiads is not such a big thing, but there is still. I mean, when I reached roughly the age, there was. Now it's much more. In place, but at the time it was one of the first years where they were creating a competition to try to enter the Math Olympiad, international ones. And I think I was so bad. I don't think I even solved one of the 6 problems. So of course, when you never solve this type of problems and you arrive and you have these 6 problems in front of you, I just sucked at it completely. So you see, you can be a fairly successful mathematician while being a terrible Math Olympiad student. So for me, it was too early. Probably I was not mature enough in my head. It was not my type of mathematics. Like, for instance, the fact that you have a time pressure, right? I mean, you need to solve the problems in a certain time, for instance, was something that was not matching me. So there are many examples of very successful mathematicians who were extremely successful at Math Olympiads. But if I have a message, is that it's not, it's neither a sufficient or a necessary condition. So it's not necessary. You can just not do Math Olympiads, or even worse, being super bad at it, like me, and still being a successful mathematician. And it's not sufficient also because there are very successful Math Olympiad students that never really become mathematicians, because it's a different thing. mathematics, you have to sometimes wait for years before solving a problem. And Math Olympiad is really learning to solve quickly. So in some sense, you get your feedback very quickly, right? So it's something that you have to cope with when you are a mathematician, is to accept that you will not get feedback quickly, that you don't even know whether you will ever solve the problem, if anybody will ever solve the problem. So this requires different skills. So Math Olympiad is a cool thing. I think it's a cool also advertisement for mathematics among young students, but it should not be taken as something that you have to succeed to become a mathematician. Don't worry if you don't succeed. You are still in good shape to become a mathematician if you want to. Now, the second question was about partial differential equations and things like that. Let me say that one thing I like very much in statistical physics, in my field of research, is that you have to borrow from many different areas of mathematics. It's something where you are very broad in the scope of what you need. So partial differential equations typically are among the tools that we need. In particular, you see, just to give you an example, if you look at what we call thermodynamical quantities of a system, pressure, energy, temperature, and so on, they are usually related to each other. And you can in particular look how they vary when you vary the parameters. For instance, the temperature and the pressure if you take water. And there you have actually a partial differential equation appearing. Like if you vary in t, it's going to vary in a certain way. If you vary in h, it's going to vary in another way. So you have connections between partial derivative in temperature, partial derivative in pressure, for instance, and you actually want to juggle with this type of formulas to try to get some useful information. So yes, I use this in my life, like many other fields of mathematics, and for that, statistical physics is a super cool field because you really have to learn a lot of different math, which is something very enriching.
Wonderful, thank you. Next question from Back Pro. Can you give advice to math lovers? Same question for Hamza. What's your best advice for the coming mathematician and generation?
So here, I mean, to try not to go to the, I mean, to answer maybe your question, I understand these two questions maybe as math lover, as maybe somebody not necessarily doing math and just enjoying math as a hobby. There, I think nowadays, and thanks to people like you, there are many videos that you can watch of very interesting mathematician, much more interesting than me, by the way, that will tell you about math in some very brilliant way, so you can learn about math a lot from the perspective of people who do it, which I think is something very interesting. And the second thing is that you find more and more, but this is a little bit more difficult, but again, I think that mathematics is something you enjoy because you practice it. So you need to find, in some sense, and you can find a little bit online, books where you have kind of problems that don't necessarily require a lot of math background. It can be, logic problem, for instance, or problems that are not involving too much formalism. And there you can just try and practice on these problems if you want to just enjoy this as a hobby. So that's for the first question. For the second interpretation of the question, where you are really talking about young mathematicians, let's say PhD in mathematics, postdocs, or things like that, I think there again, it's difficult to claim to be a good example and give good advice. But I think one thing that for me worked very well is that I feel that it's important to have several levels of problems you are working on. It's not good if you have only a super hard problem, very low chance of success, very high gain. Well, it's good to think once in a while on problems like that, but you should not make your whole young career thinking about them, because if you don't succeed, well, you are left with nothing. It's not good, on the other hand, to only look at, very high probability, so very low risk, very low gain, because in some sense, low risk means that you are going to solve many of those problems, but it's not really going to show your actual level, because you want to be showing that you can, prove problem of this difficulty. If you only solve problems there, people will think this is your max level. So you need to kind of not spend too much time on low-hanging fruits. So usually I recommend to my students to have 3 problems. One problem that they are kind of certain they are going to solve, and this, once in a while, so it takes like 3 months or 6 months, and they solve, they write article, and they pass to another low-hanging fruit. Then I recommend to have a problem that they think is kind of their max level, roughly, that they have doubts they can solve, but maybe they can solve it. And then you need to have this very difficult problem. Probably you will never solve it, but just, once in a while, when you are in the bus or when you are under your shower, just give it a thought once in a while, because thinking about a problem that is too hard, maybe you will never solve it, but it's going to, again, you are maybe going to fall in love with this problem, and you are going to learn a lot from trying to solve it. Either new math, or you are going to learn from your mistakes, new insight, and who knows, once in a while, you actually even solve it. And there it's like bingo.
So I have other questions. I have same question here. So from Shayma Khawater, I am very happy to see you. My question that how can we do this connection between these 2 science, for example?
With what? I didn't hear. With
maybe talk about the link in physics and maths.
Yes. Okay. So between these 2 science, these 2 type of science. Why? How you make the connection? Well, first you need to find a common ground, and the common ground in the case of statistical physics is that you are both describing the same type of thing, the phase transition, for instance, of magnets. This is the same for both. It's the same motivation. But then you need to find 2 different angles of attack, in some sense. So on the physics side, it's going to be the experiment, or it's going to be, okay, maybe you make a model, but in physics, you are allowed to just describe this model. You don't need to prove every single thing you do. You need to give like strong evidence. It's not foolproof. On math side, you need to prove everything rigorously. So of course, you are going to say much less, right? It's harder to prove everything. So you are going to manage to do less. So you see here, for instance, there is a good example of a microcosm, which is efficient because you have a common goal, but you have 2 kind of paths to it. One, the physicists have this thing that they just need to describe and give strong evidence, so they can go much faster. They are in some sense pulling the car, right? And on the other side, the mathematicians, they are trying to kind of be sure that the car is not going to go anywhere and break. They are kind of repairing the car, as it goes, trying to be certain that it's a safe car by proving things. So when you have this type of good synergy between math and physics, there is a natural community that creates in the middle, if you want, in between. Sometimes connection between math and physics come in different, then in this type of things, it's going to actually have nice consequences, which is that the physics problems are going to, in fact, trigger new ideas on the math side. When you try to solve, when you try to prove what the physicists say, it's going to make you think about new mathematical ideas, new mathematical concepts. And then once you develop these new mathematical concepts and you explain them to a physicist, well, that gives him a tool. And this tool, he can use it to, imagine more and more phenomenological behaviors we can help him imagine what's next. So there is a good synergy, like a ping pong, if you want, between the two disciplines. Once you have created this kind of area where everybody is going in the same direction.
Thank you for these questions. Maybe there is some two last question from Dina bin Namara. What's your project for future? Maybe.
If only I knew. If only I knew. Because I mean, this is one of the things, right, with science, is that you are sometimes led to places you don't expect. And in my case, it happens a lot. Like, as I said, I'm kind of good at creating new ideas, but I'm actually, usually these ideas come and I'm like, okay, where is it leading me? Because it's not at all what I thought it would be. You know, you create a monster, it's Frankenstein, right? You create the creature, but then it works on its own and you are kind of... So for me, it's difficult to know where I would be going. The Ising model is one, let me try to answer, Stephen. The Ising model is one model of statistical physics. It describes ferromagnetism. But I mean, there are many other models of statistical physics. And obviously, I would like to kind of connect them as much as possible to some percolation models, or use the ideas that I developed in percolation theory to understand better other problems. You have beautiful problems, you know, for instance, Anderson model is a model for the localization of electrons in a random, in a disordered medium, for instance, a medium which is not homogeneous. These are beautiful questions. I would like to think about them, even though I'm an enlightened amateur for now. I like the question, but I never really worked on it. So this I mean, I only started 2 years ago, so it's very new for me. And this is an example, for instance, like trying to push further. There are so many phase transitions, so many different behavior. How far can you go with ideas from percolation theory? How unifying you can be in understanding different phase transition using the same ideas, you know, again, trying to make bridges between different areas. So this is clearly something I would like to be doing.
Last question en French. Existe-t-il vraiment des systèmes aléatoires?
So are there really truly random systems? This is a huge question. I mean, this is a question that would require another life, probably. Because I mean, does randomness truly exist? Right? I mean, that's basically the question. And there are different level answers. So you see, when you toss your coin and it falls on tail or face, as a human, you are going to say this is a random outcome. Right? This is clearly random. Because what? Because you cannot predict it. But in fact, if you are a computer, if you analyze, you know, with a very high frequency video, you slow down the thing, you look at original speed and place, you know, you can just use the laws of gravity and I mean, Newton laws to just predict that it's going to be on tail or face before it hits the ground. So this is a false randomness in some sense. It's just apparent randomness because you are bad at predicting what happens. And many systems in everyday life are like that. They are in some sense too difficult to predict to actually consider them anything else than random. So randomness at this level doesn't really exist in some sense. There is randomness at a certain level, at least if you believe in quantum physics and in the certain, for instance, in Copenhagen interpretation of quantum physics, when you go to the level of infinitesimal scales, for instance, whether a photon is going to, you know, there is this famous experiment with two holes and you throw photons. Now they even managed to do it in a lab. Originally, it's an experiment proposed by Feynman, the very famous Nobel Prize physicist. It was a thought experiment, but now they even managed to make it as a true experiment with new lasers and things like that. So they shoot photons one by one at a wall with two holes. And basically, you know that photons, before being measured, they act like waves. But as soon as you measure them, you can really say, okay, the photon reached here or here or here or here. And they look at basically the pattern that you see on the other side of the wall. And the pattern, if you look at where the points hit, you are going to see interference. And interference there is completely, basically excluding the possibility that you can predict when you shoot the photon in which one of the two holes it's going to pass. It's impossible, basically. If you could predict like that, then actually you will not see interference on the other side. So that means that the photon truly randomly chooses which hole it's going to take. And this is true randomness. So this is a truly random system. So that's just to say that at least if you believe in quantum physics, and actually people will even stronger make a stronger claim that even if you don't believe, the phenomenology is excluding even the possibility. So it has to be that there is randomness in the universe at the infinitesimal scale. This is a second kind of answer you can provide. And let me give you a third answer. The answer of the probabilist. That even if randomness would not exist, even, you have this kind of apparent randomness, you have the true randomness in quantum physics, but imagine, in fact, the world doesn't work like that and there is no randomness at all. There is still a randomness you can introduce, kind of an artificial randomness, a randomness in your mind that you use the theory of probability to create, to say, I'm going to pick at random an object. This object is just an object in my mind. It's not bound to be following the rules of physics. It's an object in my mind. But I'm allowed to imagine that I pick it at random, as a mathematical tool to understand what is going to happen. I would call it maybe artificial randomness, in the sense that it's only me as a mathematician. I create this randomness by using the probability theory. And that's what happens for Ising, for instance. I'm creating randomness, I'm creating a random object. When I look at the porosity of a medium, I create a random graph. And then I study this random graph. So 3 levels of randomness, like apparent one, true one, and artificial ones. And I think any of those are actually very cool type of randomness.
So thank you so much, Professor. I think there is a lot of questions. I'll make it so much. Thank you, Professor, again. Thank you to all the followers, and let me meet you at another opportunity with another scientist. Thank you, Professor,
Thank
for
you very
accepting
much for
the
the invitation.
invitation.
Thank you, everybody, for listening and for the questions. Bye-bye.
We hope that you will be visit us in Morocco one day.
Yes, that's a deal.
Thank you so much. Thank you,
Bye-bye.
Professor. Bye-bye.